next Wednesday. Okay. All right. So what is not clear with Dirac-Frenkel? Yeah. What is not clear?
What does the Dirac-Frenkel variational approach? What does it do? Right? Like I don't even. I mean, the only thing I can think of is to plug in a bunch of stuff and beat it around with algebra and see what happens. Yeah.
Well,
but I have no intuition.
But you didn't answer your own question, right?
Pardon me?
Your own question was, what is it good for? What does it do, right? Why would you do that? Oh, you said you're preparing your alcohol to get drunk, I presume, or sell it, right? So there is some pleasure involved, one way or another. Yes. But with Dirac-Frenkel, where does the pleasure come from? So, as with any variational principle, you want to solve some problem with the amount of resources that you can afford.
Yes.
Right? It's like with alcohol again, you don't go to this LCBO, you do it yourself because you don't have maybe money to go to LCBO, right? So the same here is that, say you have a time-dependent Schrödinger equation to solve, right? And then you want to represent your xt as Gaussian that was given, right?
So is that in general with the Dirac-Frenkel approximation, or is that just for this question?
It's for this question, okay. And that is kind of your resource that you have at your disposal. Plus IPQ divided by 2 times n, that depends on alpha. Right, so there are many ways you can write psi, right? The true psi is not equal to this exponent, right? True solution.
So this is an ansatz.
That's an ansatz, right? So the true psi requires you to have a complete basis, right? That means infinite number of parameters, and just let it go according to time-dependent Schrödinger equation. If h, say, is not time-dependent, then the simple solution is you have this propagator and you're acting on psi x0, which you need to have always to obtain xt. And this is exact, assuming that h is time independent, Let's focus on time independent case for now. All right, so this is exact, but to do that, you need somehow to calculate this matrix. And to do it exactly, you can do it only for some simple model problems. For some simple model problems, the way to calculate it would be to diagonalize the Hamiltonian, and then exponent of the diagonal matrix is. So say you build some representation in the basis set of eigenstates of H, right? And then what you can do is you represent your psi of x0 as linear combination of these basis functions. Right, and then action of h on this function will be very simple, and that exponent acting on psi x0 will be Cn ENT, right, sum over n phi and x. Right, so that is psi of xt. Very straightforward. It's because your Hamiltonian in this representation is diagonal. So h becomes u, e, u dagger, and then exponentiation of Hamiltonian minus e h t becomes u exponent of minus e t, u dagger, right? And then these matrices, they just transform, well, whatever function initially you have into the basis, and so then if you multiply by psi x0, you represent psi x0 in some basis, and then this will be the coefficients, right, you have here. And so then the Hamiltonian is acting in a very simple way to these basis functions, and then you go back to whatever representation you started with. All right, so to be complete, this U is the matrix that transforms, say, if you don't know initially what these eigenstates are, you know some phi n's, some basis, and then you represent your psi x0 as dn phi n's. Right? Then the U matrix transforms the D coefficients to the C coefficients. Right? So the matrix form. But you can do that without all these U matrices, just by writing down psi x0 as a linear combination of eigenfunctions for the Hamiltonian. Right? For that, of course, you need to solve this problem. Now, in some cases, solving this problem is difficult, or, well, we are looking always for more alternative ways. One of the alternative ways is approximate solution. And the reason for looking for approximate solution is that this program you still cannot do exactly, because to do this program exactly, you need to have summation over all infinite basis function expansion, right? And so practically, you will always consider the approximate, and so now why to worry about finding these functions, expanding your initial function in them, if it's still going to be approximate at the end, right? So the amount of resources you have would correspond to the number of coefficients you can actually carry on, right, in this dynamics to produce your approximate psi of xt, not the true psi xt. And then also the incredible large cost could be coming from this part, where you need to solve time-independent Schrödinger equation and find these phi n's. And then expanding your initial function in this, it also involves some integration of these basis functions with the initial functions to get the coefficients, right? So, and at the end, it will still be approximate. Now, alternative way is, all right, say you feel adventurous and you decide that you can guess what the physics will be, and you usually feel adventurous when you see potential, like this Hamiltonian, the kinetic energy plus potential energy, right? And p squared divided by 2m, and the v, say, is kx squared divided by 2. So this is parabola, and it's possible to show that for this model problem, there is a width of the Gaussian that corresponds to the frequency of this parabola. Frequency would be square root of k divided by m. You can transform this Hamiltonian in a slightly different variables. Q, which is square root of m multiplied by x, and then in that this new variables, new p, that would correspond to the differentiating in respect to q, squared divided by 2 will be like this. All right, that's the form that I think I used in that. Oh, I didn't supply the potential, but anyway. So if the width of the Gaussian corresponds to the frequency of oscillations in this harmonic oscillator potential, then you can solve problem for this model problem exactly, and you can find that Gaussian will stay Gaussian, essentially. Okay, so that will be the true solution. Now, that means that the full quantum dynamics that you could obtain by expanding your, say, initial Gaussian is given. It's your psi of x0. You expand it in as many eigenstates of harmonic oscillator as you need to, well, expand it properly. Then you would propagate all this, well, you supply the coefficients with these phases, and this becomes kind of a function of time, right? So this coefficient in front of that eigenstate. And so you will carry all these phases to reproduce the dynamics that you can capture actually by alternatively doing the Gaussian propagation, for which you need only p as a function of t and q as a function of t. There's parameters inside of this Gaussian. That
Generalized momentum and position?
well, yeah, I guess I may be using slightly confusing variables here, because x, I switched to q, which is still variable, but say, to reserve q for the parameter, we say big X and then big P corresponding to the big X. So you have big X here, right? And then with this, you can start with the wave packet like this for some P and Qs. And then all axes here will be big axes, our variable, spatial variable. And P and Q, those are the only functions of time that you need to propagate or know their dynamics as a function of. Like essentially, you will get out of this Dirac-Frenkel principle, you would get differential equations on P dot and Q dot, and they are equal to some functions of P and Q, and this one is some other function of P and Q. So solving these differential equations, you can obtain the P and Q as a function of t. Putting it inside of this Gaussian, you will generate what the psi of x at time t will be. And for that, the only price is you are, well, solving differential equation for two variables. Okay, so essentially you're propagating only two coefficients in front of, instead of, I'll say 10. That you may need to represent this wave packet as a linear combination of eigenstates of harmonic oscillator. Okay, 2 versus 10, maybe not such a big deal, but if you go to the more dimensions, right? So say you add second dimension, third, fourth, the number of eigenstates that you need will go 10 to the power of dimension, exponential growth. While the number of coefficients or momenta and positions will grow linearly, because it's a position of multidimensional Gaussian, right? So, and momentum of multidimensional Gaussian. So for two-dimensional Gaussian, you need two momenta and two positions. Okay.
So Dirac-Frenkel provides the differential equations.
That's right. For P and Q.
And then you can solve them and plug them into your gas. Or I'm just confused where our ansatz comes into the
well, the ansatz comes because you allow this function, to change with time only through these functions, P and Q. Say it wants to do something, but you allow it only to do something else. Right?
Okay.
So the simple example would be, all right, I said here that the Gaussian should have the width corresponding to the frequency of vibrations on that harmonic potential. Now, you take a flat surface that is also harmonic potential with the width with the frequency 0, right? And then there is a mismatch. If you have a finite width Gaussian, then the width of the Gaussian, alpha or omega. So, okay, so alpha is reserved for the width of the Gaussian, is not equal to the width, which is sometimes called coherent width, because this motion is like a coherent oscillation. So that means that Gaussian is not changing its shape. Nothing actually changes with for Gaussian. Like it's just going back and forth, right? Now there is a mismatch, and that mismatch leads to thawing, essentially, that the Gaussian becomes wider and wider and wider and wider. Why does this happen? Because this in the momentum, like essentially what the momentum of each part of the Gaussian is, These guys are corresponding to, say, higher momentum. These ones are lower momentum, and so they distribute over the space. And so some parts of the Gaussians move faster, some parts move slower, and eventually it kind of becomes broader and broader and broader. Okay? So with this construction, with this ansatz, alpha is not something that you vary. Right? So it's not going to capture that broadening. Okay? So the true dynamics will be like I plotted here. It's going to, if say you have some initial momentum and initial position, then later in time, of course, the momentum will change. Momentum will be the same because average momentum will be the same because there is no force. It's a flat surface, right? Position will change of the center somewhere, but the Gaussian will stay like this. It's called frozen Gaussian. This construction called frozen Gaussian because alpha is not varied, right? But in real life, the width must vary to reproduce the true dynamics. Okay. And the general rule here that is derived in tenor is that if you have general Gaussian, here there is also somewhat constrained because what tenor considers the general form of the Gaussian has alpha, PQ, and gamma, the phase. Right? If you let all these four vary, then you end up with a representation of quantum dynamics which will be true for any up to quadratic potential. If you go beyond quadratic, then these four parameters will not be enough. Okay? Now, for quadratic potential, you need to match this. If you want to work with the frozen Gaussian, alpha is frozen, and then these conditions are just keeping things normalized through the dynamics. Then what you have is that you need to match with your width the frequency of the parabola on which you are moving. If there is a deviation or potential is not harmonic at all, like a Morse potential, for example. Morse potential is something that chemists like to use to represent the stretch of the bond in diatomic molecules, because it's kind of related to a general question why things break, right? So if we think about energy growing quadratically with the displacement, that means the force that you experience when you stretch your sweater or your hair, right? So that will be linearly proportional to the displacement. And so this essentially means the infinitely stretchable rubber band, right? But we know that things are not like that. They break, they snap. And so to have that, you need to have a deviation from that harmonic behavior. And the Morse potential is the one that, some simple model that gives it to you. Because then you know that once you pass this point, actually the energy price for stretching is lower, 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 and eventually it's kind of very small. Or, you're not paying any energy anymore, right? And more interesting consideration can be done that if you have solid, right, with like essentially atoms on the line, right, then why things break is still a question, because if you think about interaction between every piece, like even like a Morse interaction, what you would expect is like you need a lot of energy, right, to stretch this whole thing, because yes, you will pay less energy later in the game, right, but to get here, it's not only one bond you need to stretch, it's all others as well, right? So even with the Morse potential in mind, if you think about the solid as a one-dimensional, again the simplest model, one-dimensional polymer, right, then it's still not clear why can we use finite energy to break things, right? And the answer to that is very simple, actually. If you even consider just the two kind of monomers or two cells in the infinite chain, is that initially what happens, you put some energy, you want to stretch, and though you get, say, delta x here and delta x here. And since it's a harmonic, it doesn't really matter whether one is larger than another. You get, oh, pretty much they're going to be the same, right? But then at a certain distance, once you pass this point of the kind of inflection point, right? Then energetically, it's more favorable to contract one and expand another. Because the price you're going to pay for expanding one will be smaller than the energy you're going to gain by by going this way on another. Right? So in a harmonic case, you will never gain anything by stretching one bond and contracting others. But in an unharmonic chain, you will gain, like essentially this is a steep part, this is a shallow part. That means after this point, you're gonna essentially gain a lot by contracting, right, of some bonds and stretching others, right? So this proportionality will benefit the overall energy, and that's why when we put enough stress, eventually one bond snaps and others contract, and that's a kind of win. It's like essentially sacrifice of one for the sake of others. Right. All right, so that's about potentials, and that's the ansatz. So now you can see that even in just a general quadratic potential, this doesn't solve the whole problem in general, but it could be pretty good. It could, for some cases, just with P and Q, you can get the total dynamics. But in others, you can get just pretty darn good dynamics.
So in our questions on the assignment, we don't know what the potential is.
Yeah.
So how do we get around?
Well, you just keep the integrals with the potential in the kind of implicit form, right? So since you don't know v of x, the integral over x cannot be taken explicitly. But since you got extension, right? So why don't I define v of x and kx squared divided by 2, and you solve.
So we're looking at
Yeah. Yeah.
Which ties into the next.
What?
Which ties into the next assignment.
Yeah.
So the problem is like the way at least four of us have been doing it is kind of like plugging and shoving, like doing these very difficult integrals and difficult integrators in Mathematica. Is it supposed to have a nice easy solution, or is it supposed to look?
Which integrals are difficult? I specifically try to choose examples where integrals are simple. Which integrals are difficult?
I think, like my experience is that none of the integrals are difficult, like in the sense that they were polynomials. They just got kind of long. Yeah,
They're not actually hard.
but they're just long polynomials with interesting coefficients.
So the
Interesting
answer doesn't
varying
look like
functions.
what we expect to be nice.
Well, I can tell you the answer for the question with polynomials. Like, I believe that's the second problem in the first section, where psi of x for particle in the box is kind of coded with x minus L, right? That answer is just this nice answer.
We're talking about 3.1, like the equation for like.
Wait, but 3.1 without potential, you don't have integrals to take. The space integrals, they cannot be taken simply because you don't have potential, right? So you keep them like as some function of what, t then? Or, yeah, t functions are going outside of the integral, right? So the integral just becomes a constant.
That's what I said to you, nobody believed me.
Wait, why you said to evaluate them?
Well, if you have a potential, you can evaluate them now.
But like, do you separate the potential out as like a separate integral or evaluate the rest?
Yeah, you're right. So the time part can be evaluated. Yeah, so that's what you're talking about, the time part that is difficult. It's just a Gaussian integration. It cannot be difficult. It's one of the.
It's with all the constants and the way it comes, when you simplify it all together, it becomes a very long expression.
Mhm.
You know, rather than getting
But you have mathematical on your side.
yeah.
Yeah.
I used to be when I was, you know, if I was plugging in more than one.
Consider this as a kind of an example. Well, you still need to know how to use Mathematica properly, right? So that's an exercise to to master Mathematica.
Ugly bugger at the end? Like,
Sorry?
Is it the final expression for dq over dt and dq over dt supposed to be like hideously ugly with the 100 constants and various things?
100?
Well, you see, we don't usually ask this question in science. Well, what question we usually ask is, okay, so if we're doing something that hasn't been done before, how do we check the result is any good, right? So you kind of get into that question, but there might be no kind of internal beauty of the result. It's just either right or wrong, right? And how do you check that? Well, you can code it up and see what dynamics looks like, and then see whether it satisfies some energy conservation or other constraints. Okay, so that's the only way I can offer. Is
How will we check if it does energy conservation?
well, you can calculate energy at every time step, right?
Are you talking about conserving energy with the integrator?
Yeah. So when you find the Q and P, right? So then you have a psi at every time step, and so you can obtain that beast and calculate energy for the Hamiltonian, and energy must be conserved. Okay. So there is a way to show that energy will be conserved. Good exercise.
So do you want us to not do the problem with v of x as random? You want the kx first?
Yeah, sure. Let's do that, since you have already extension to do more integration. Yeah.
No, maybe it'll make it nicer.
Yeah, maybe it will make it nicer.
Yeah, when I got rid of these like completely, the solution was at least ready to write it on one line. It kind of
So but the solution you would expect to be close to what you have in the classical oscillations, right?
well,
Because it's a quadratic potential according to Ehrenfest theorem, it should work, right?
Because it's less than, like the third derivatives and higher are
Yeah, right.
classical and quantum.
Right.
That's part of the assignment. I had like a nice eureka moment.
Uh-huh.
I finally understood the quantum forces and all that with it.
Good.
Yeah, I don't know, it was pretty exciting.
So maybe at the end of the course you will see the quantum world in its full glory.
That
Yeah.
might be a little bit ambitious.
Anyway, yeah.
Oh, really? It might be way nicer if you actually did that.
Yeah.
I hope you're right.
I'm hopeful.
All right. So are we ready to
Oh yeah.
immerse into non-adiabatic dynamics?
We also have to expand it to more dimensions. Is that just like doing the same thing but like way out there again?
Well, there you have coefficients.
Yeah.
All right. So and there you can just the point of that exercise was just to see what kind of differential equations you're gonna get. All right. So
we can take it similar for matrix approach.
yeah. So there will be matrices involved.
Yeah, those are the same thing from we can set it up as a distribution. That's still going to be pretty ugly.
wait,
But this
Oh, you don't need to solve them, right?
It's still going to be ugly,
I
but
understand
yeah.
with the sum.
Huh?
No, it's just like because if you were asking for like the I terms, not like for specifically C1, C2, but more just for like CI dot instead. And I found you can kind of find those without actually doing the sum and finding C1, C2. Maybe it's wrong.
No, the equations for CI dot will involve naturally P and Q's and C's, right?
But I found that like C1 dot would only involve terms that have ones. So you can, it won't involve like C2 or QX2 or.
But what is the potential that you're considering?
It's arbitrary.
Huh?
The it's arbitrary because we didn't define
is it arbitrary xy potential?
Yeah.
So then I don't see, oh wait, then I don't see the reason why. Why would you have, for C1 be decoupled from the C2, the Hamiltonian matrix elements with different basis functions, sorry. So say you have Gaussian 1, Hamiltonian Gaussian 2, those terms must be 0. Then you would lose the connection between C1 and C2. But I don't see the reason why they should be 0.
Okay. Yeah.
Yeah,
Maybe
so just,
somehow it came out in my math that way, but I don't know.
no.
I feel like maybe my thinking is right. But rather than trying to use the Dirac-Frankel variational principle explicitly, and just using our ansatz to solve the series of integrals and then find a bunch of differential equations, and then you can solve for the differential equations within. Because each differential equation relies on other differential equations.
Yeah, it's a system of differential equations.
So you can have a whole solve function set up in order to solve for all 5? Some number of them.
6, yeah.
Which is arguably a time-intensive process. Would it be better to construct it, like I was saying, as a matrix and having a series of representations like that, solving them?
I don't care which representation you put to your result as long as it's correct, right? So, and by correct means that you define every variable you write, right? So if you say C, P, Q, then you need, or some other letters, and matrix form, non-matrix form, doesn't really matter. So as long as everything is defined in terms of P and Q and C's, right? So that you can actually code this and check whether it's correct or not, then it's fine. Right, so, and I'm not asking you to code this, so that would be one way to finish this assignment to the numbers, because solving these differential equations for some particular potential is really, maybe impossible even, right? Because no one says that these differential equations for P and Q, they will be analytically solvable. That's why we, after all, use this ansatz or Dirac-Frankel essentially allows us to set up the ansatz based on our physical intuition, saying, okay, potential looks like harmonic, so the Gaussian should work, right? And then I cut the price of or cost of the calculations because alternative to the Gaussian will be, expanding in some other basis, right? And that basis may be just too long, or in a sense that too many functions to capture the physics that is happening there. So Gaussian are good for molecules, especially because things are quite harmonic in many cases. All right, and Gaussian is, I guess, the most frequently used non-linear ansatz. Okay, so the point of this exercise was to show how to do things with non-linear ansatz.
Last question.
Mm-hmm.
For 3-2, should we also assume a potential, harmonic?
No, 3-2 just general. That's just, otherwise will become too lengthy. And the whole point of 3-2 was to be able to treat more than one dimension and more than one Gaussian. So it's just essentially exercise in differentiation. Right. So that's why I was surprised to learn that you have troubles with integration, because at least in Dirac-Frankel you don't need to integrate much. It's just pretty much differentiation of functions with respect to parameters that are P and Q. Okay? Good. All right, so now back to non-adiabatic dynamics. So when I promised this is the last chapter on the non-adiabatic dynamics, because then it becomes kind of too specific. And we need to move on to other things like perturbation theory and relation to spectroscopy. So, but just to finish the non-adiabatic dynamics, I wanted to talk today about non-crossing rule and diabatic representation. What else? And yes, those are the and conical intersections. Those were somewhat announced previously. Or okay, so the whole, again, the reminder, the whole problem here is that we have a dynamics of a system that consists of two types of particles, electrons, nuclei. Electrons are faster, nuclei are slower. That's the usual mantra. But well, the reality is just electrons have a larger energy scale, and that's why what Born and Oppenheimer suggested, let's just freeze the nuclei and calculate first electronic states. EI R, then our energies will depend parametrically on big R's. And then and so once we solve that, we can then obtain coefficients for the chi part, which depends on R and T in the dynamical processes. Or if we solve time-independent Schrödinger equation, then the T will disappear out of everything. And this, then the chi equation. The chi equation we obtain by taking the whole Hamiltonian, which is the nuclear part plus electronic Hamiltonian, right? And then we project this Hamiltonian onto the basis of electronic states. Project means we take H and we build the phi E, integrating the electronic variables, phi J, electronic, and then naturally you get chi here of R and T, and there is a sum over I, and you will get something like I guess chi J for T, differentiate with respect to time, multiplied by IH bar. All right? Because our initial equation was H psi equals to I d psi over dt, H bar. Right? So then we project with electronic function J from the left, and then it was killed here on the right-hand side, and then on the left-hand side we have a matrix of Hamiltonian. And so for just a situation when we have two electronic states involved, and that situation is quite typical because, as I was saying, this energy scale of electrons, it's relatively high. So you have, say, electronic levels, and then the nuclear levels, they are separated with smaller energy distances, right? So then if you shine light on the system, then you know approximately that you probably can cross this energy distance, right? And state phi 1 and phi 2 are involved, but not phi 3. Yeah.
So you're saying if you shine light, like if you give the system energy,
yeah,
it's going to send an electron to a higher state?
Yeah.
That's what you're saying, but it's going to be too much to send the nucleus to a higher state. Is that what you're saying?
Well, with nuclei, we will with nuclei, they will be kind of sent also. So you have chi, say, some wave packet on the ground state, and when the excitation happens, we'll consider that in perturbation theory, because this interaction with light can be easily considered a perturbation theory approach. But the outcome of that consideration is that essentially we get the same wave packet, because light is kind of very fast compared to all the degrees of freedom in the molecule. So then you build the same wave packet out of the just vibrational states on a different electronic state, right? So it's without much of the distortion. The same wave packet will be on the second state. So the chi2, spatially at least, in the nuclear variable space, right, it will be the same as chi1 that we started with. Okay, so usually for the chemistry, the light is considered to be very fast, and then our initial dynamics or our initial wave function for this kind of processes may be related to, say, later crossing of levels, right? So that the dynamics goes like somewhere close to the intersection, and then something happens, like system goes from the upper state back to the lower state, but for the different nuclear geometry, because here we have a nuclear geometry. All right. So for that process, we say in the basis of our electronic state 1 and 2, our initial nuclear state will be our chi-r at 0 time will be just chi-1 will be 0, because we already pumped our system to the second state, and chi2 will be something, right? And then eventually when chi2 will evolve close to the intersection region, then through the so-called non-adiabatic terms, you will have a population of the first ground state, right? So this will evolve into chi1 RT, chi2 RT. These are two components in the total functional representation of psi, which are chi1 phi1 plus chi2 phi2, right? It's like with vectors. If you have a vector in the two-dimensional space, V, you can write it as V1, V2, two numbers, or you can write it as V1 number multiplied by basis vector E1 plus V2 multiplied by E2 vector, right? And these are basis vectors. So in our consideration, phi1 and phi2 are our basis vectors. And so if we write things in a vector form, right, then we skip them and we just position them as some entries in the vector format, okay? But they are themselves functions. So what happened here, we discretize electrons. So we consider discrete representation of electronic variables, and we still consider in the continuous representation for the space, for the nuclear variables. Yeah.
So when we're writing vectors with the parentheses, we sort of lose the information of the basis functions?
Or we need to keep it like it's implicit, essentially.
Okay.
But it must be somewhere. Otherwise, this is meaningless.
Yeah.
Right. The same as if I say 5, 6, that's the vector. It's meaningless because it can be 5 with 5x, 6y, or vice versa, 6y or 5y, 6x, or some other vectors. So you can rotate system, of course. So essentially, this format requires the basis to be somewhere in the back of our head.
And the basis, the thing that I'm thinking of is if we take a derivative, does the basis change? Because like Cartesian coordinates, the basis
doesn't change.
So we don't have to worry with derivatives.
Yeah.
We can just leave it in with.
But here it's more like a curvilinear system of coordinates where the basis is changing.
Yeah.
So that's why there is sometimes physicists like to call it long derivative appear, where the derivative of the quantity is equal to the derivative of the quantity itself plus the component that comes out of the basis differentiation, right? Yeah. So, and then you can define it as a long derivative, essentially.
I've never heard that term before. But
well,
definitely
It's in, I guess it's in general relativity, that sort of subjects where you use the curvilinear coordinates a lot. Yeah, so then if you have derivative with respect to r, but your basis, which is electronic basis, it depends on r, and your quantity, say this is your quantity of interest, right? So it also depends on big R. Yeah. Then differentiation will be just as a chain rule, right? So you have this df part chi plus the part where you have phi d chi over dr. So then you can say that derivative operator is defined in this space as derivative operator plus multiplication by this term.
Which is the derivative of our basis factor.
Right. Or if you, well, usually if you work with the derivative in the space of chi, right, then you should not have phi there, because phi has a small r dependence. How do we get rid of small r dependence? We usually have the conjugated quantity integrated, right? So we integrate out phi, and true derivative in the nuclear space would be equivalent to the following operation. So it's like phi e star d over dr phi e, and that whole thing is acting on chi, and then this is equivalent to having as a chain rule or as a differentiation of the product, this differentiate this and that. So when this differentiate the chi, these guys just give you 1 because they are normalized, right? So then you have d over dr plus the term that is like a function of r, and it's dr phi star e d phi dr, right, times chi, right? So this is your long derivative because it has a derivative itself plus the term that appears because your basis depends on r, right? So the situation is actually the functional space makes it all very looking very complicated, but in reality, if you think about this as just a kinetic energy part, right? So what you have in the kind of chemical set of mind, with these surfaces, you kind of consider a chemical reaction from A to B, right? And the chi, the wave packet, kind of defines the dynamics going from A to B. And the kinetic energy of that that kind of object depends on the kinetic, like its own kinetic energy plus kinetic energy of the surface on which it's moving, right? So the real life example would be if you are not running on the static surface on the ground, but you're running on the moving platform, the total kinetic energy will be kinetic energy of the platform plus kinetic energy of the runner, or you in this case, right? So in this case, this is the kinetic energy of the chi, or part of the kinetic energy. You need to have second derivative, and this is the kinetic energy of the platform. Okay. Yeah. So it's very simple if you toss out the functions or you interpret them in a kind of wave packet way that kind of describes the chemistry. So rearrangement of nuclei, that's what they are. Rearrangement of nuclei from the point A to point B. Cis trans isomerization, that sort of stuff. Okay. All right. Good. So now, I don't think I've written anywhere the total expression for two-state problem, because the two-state problem is somewhat simple to write. The expression for chi, right? So the expression would be there's a kinetic energy of the nuclei plus so-called tau11 term, tau12 term, tau21 term, tau n plus tau22 plus the potential energy term E electronic 1 R 0 0 it's 2. Right, this is our now Hamiltonian for two-state problem, and that Hamiltonian acting on chi1, chi2 should produce I h bar d over dt chi1, chi2. Right? And then tau1 1 is, oh, I can write the general expression. Tau ij is equal to phi I, or derivative with respect to r, phi j. And then there is the part that comes out of h squared divided by 2m. Because these parts, they're derivatives, they're the same derivatives as the kinetic energy, and of course they had h bar squared divided by 2m. So it's a kinetic energy of nuclei, and they're acting on the electronic states. Minus okay, so actually plus phi I this term is multiplied by 2, and yeah. So this is the full picture. Okay, so then Tn is minus h bar squared divided by 2m. Right, so these kinetic energies, they are bare kinetic energies for our wave packets on the first and the second state. The tau terms, they are kinetic energies of electronic states, right? That need to be supplied because electronic energies are also changing while we are moving with our chi's along the nuclear space, and this is just a potential term. They form this essentially surfaces, and if you start interpreting this in the classical terms, this could be, if you differentiate these energies with respect to r's, then it's going to be electronic forces on the nuclei. Okay. And so this model would work for, say, rhodopsin or retinal. That is a chromophore of rhodopsin for describing a vision process for the cis-trans isomerization that we somewhat mentioned, right? So the energies would be here, E1, E2. And the process of isomerization, you start with a wave packet on the upper state, and then you are solving this differential equation. You can actually use some Dirac-Frankel ansatz or Dirac-Frankel principle to set this as some kind of one Gaussian or more like a linear combination of Gaussians, and then this is just time-dependent Schrödinger equation, right? So Dirac-Frankel is going to work for it, and you will obtain some parameters of your ansatz as a functions of time. Okay. All right. So now the question is whether these surfaces can cross. That's That's one question that one may ask. Why is this interesting question? Because we saw previously that these tau ij terms, they are responsible for transferring the population from the one state to another state, right? And we saw that these terms, they are proportional, tau ij's are proportional to 1 over energy difference, right? And so if at some geometry surfaces can cross, then these terms become infinite, and that is highly effective then for the transfer of the population, all right, if you have infinite couplings. All right, so now that's the question, and the way you can approach this question in a short form is that, say, I will introduce so-called crude adiabatic approximation, which is very close to the adiabatic, crude adiabatic, or it's sometimes called clamped adiabatic, crude adiabatic approximation. And so what it means is that we find electronic function in a particular point of nuclear geometry, right? We find all of them, so it's a whole stack of functions. Oh, in our example, let's say for the two surfaces, there will be 2. And then we will consider the shift from R0 to R0 plus delta R. All right. And say in this geometry, surfaces are not, well, intersecting. So you have I2 R0 and E2 R0 and E1 R0. And then the question is, when you make a shift, is it possible to make these energies to kind of become degenerate? Okay. And the way we can consider this problem is also with electronic Hamiltonian, because these energies, or the energies we want them to be at later point at R0 plus delta R, right? They are coming out of electronic Hamiltonian. And so the way we represent, it's IE. The way we represent these true solutions for this problem is on the basis of these crude adiabatic states. Okay, we can do that. Yeah.
Yeah. Are the energies negative? Why?
Negative? No, it's just first I put them as levels, and then I try to show that we are looking at the behavior of these energies as a function of big R's. Okay. And so then, if we represent our electronic functions at R0 plus delta R as linear combination C1 or C1I, yes, times function 1 plus C2I function 2, right? So essentially what we do, we using the variational linear ansatz for representing the true functions through the functions that are crude adiabatic. They are crude adiabatic because they are adiabatic only in one particular nuclear point of geometry, right? So they are only adiabatic R0, but once we step from R0 to some other point, they are not anymore adiabatic, they are not eigenfunctions of our Hamiltonian, electronic Hamiltonian, which still depends on the big R's, right? And so we know how to solve this problem. It gives us a matrix equation with H11. There is R dependence in H11 and all other elements because I'll just write it first and then I'll explain why. Or you may tell me why. Right, so and then Hij is matrix elements with phi electronic I R0, electronic Hamiltonian at R, phi electronic J R0. Right, so we have functions that are taken at R0, but the Hamiltonian is taken at R. Okay? That's why our matrix elements, they depend on R, or equivalently on delta R, our shift. Right? And so the question is whether we can have energies that E1 will be equal to E2. Right. Oh, but for this problem, we can write down energies very quickly. Our energies 1, 2 is H11 plus H22 half plus square root H22 right? Do you follow?
Yes, but
Say it again.
where did that come from?
This part?
Yeah, like that's a quadratic formula, but I just don't see the quadratic.
How do you solve this problem?
Oh, okay.
What will determinant give you?
Quadratic formula.
Quadratic formula, yeah. Quadratic equation. So determinant of H11 minus E in diagonals, determinant product of this minus product of that. So that will be this. And also you can assume for most of the cases that's true, H12 is the same as H21 because they're Hermitian Hamiltonian and real functions, then H12 and H21 are the same, so that's why only H12 is appearing there. In non-symmetric case, it would be H12 times H21, and but in the symmetric case, H12, right? So half of the diagonal elements divided, half of the diagonal, sum of the diagonal elements plus minus, and this thing, right? Now, what does that mean? So for these guys to be the same, the square root must be 0, right? Very simple. So E1 equals E2. That follows from this condition that H11 minus H22 should equal to 0. They're both positive, right? So there's only way you can get square root equal to be equal to 0 is when both contributions are 0, right? Because they're real and they're positive. So then you have this condition and H12 equals 0. This condition. And now it's time to remember that this H11 and H21 and essentially all the matrix elements of the Hamiltonian, they're functions of R. And what we did, we started with some point where energies are not degenerate, and we asked ourselves, can we go from R0 to R0 plus delta R that spans the whole space of nuclear variables to degenerate energies for the electronic states? And the answer that this variational ansatz gave us is that to do that, we need to find delta R so that these two will be satisfied, right? These two equations, since H11 is a function of R plus delta R, right? And H22 is a function of delta R. Or you can do this. And then right? So you need to find in the whole, say if you have in molecular problems, usually people operate with 3n minus 6 variables, where n is the number of atoms, and minus 6 comes of separating the translational and rotational motion, right? Then the dimensionality of delta R space is 3n minus 6. Now, to satisfy these two conditions, you need to have, these are essentially two constraints, right? And two constraints means that you will have a space where these two equations are satisfied of the dimensionality 3n minus 8. It's minus 6 plus constraints, or minus constraints if you consider the variables, right? So that becomes 3n minus 8. Okay? Or if you are operating just with like nuclear dimensionality is n, then it becomes n minus 2. Okay? Well, this constraint thing, it's simple to explain in terms of, say you have two-dimensional space and you have an equation, right? Y of x equals y, right? No matter what equation, so linear equation, quadratic equation, whatever. This is the equation like this, and out of two dimensions, you have one-dimensional manifold in general, right? Line or parabola or whatever, right? So you have something that is parameterized only with one variable now, because that x and y, they are dependent. You cannot change both. Okay? You cannot change your delta R and stay within the space where these two energies are the same arbitrarily. There are these two constraints you need to satisfy. Okay, that's why it's minus 2. Yeah, you had a question?
So we want E1 and E2 to be the same because it simplifies our problem? I don't really understand why we want E1 and E2.
Oh, that was our initial question. Can they be the same?
Sorry?
That was our initial question. Can they be the same?
Oh,
Because
so it's just like, can they be the same?
can they be the same? Yeah. because it's not so trivial. The answer to that question, actually, if you think about diatomic molecules, right? So how many variables do we have? Internal variables, 1, right? So it's not just interatomic distance. If you put 1 there, -2 becomes -1. So you cannot have crossing of the terms, electronic energy surfaces, for diatomic molecule. Okay? Well, not generally. Okay, there are. So there are these conditions, right? But they can be satisfied also because of the symmetry. Okay, so for example, this one, if state 1 and 2 of the different symmetry, spin symmetry, which we didn't include here at all, right? So then the first constraint will be satisfied always, no matter what delta R is. Or sorry, second constraint will be satisfied always, right? And so that's the way to have intersection between different, say, singlet and triplet states of diatomic molecule. Okay, but if we consider the same symmetry, then, well, you need to have 2 variables to satisfy both of these constraints. And so that's why you can only have intersections in the cases where you have at least, in molecules it's going to be 3 after 1 variable, 3 and -6. If you put n equals 3, then it becomes 9 minus 6, it's 3, all right? So you go with diatomics, it's 3 times 2 minus 6, yeah, which is just, with diatomics, it's -5. That's why, because they're 3 and minus 5, and then here it's 3 and minus. This is for linear molecules, this is for nonlinear molecules, right? Because you have only 2 rotations for linear molecules to consider, not 3.
So it was just more of like conceptually though, we want to know if E1 can equal E2 because we want to know if there can be an intersection.
That's right. Of terms, electronic terms in this, all potential energy surfaces, because those intersections are very important for the non-adiabatic transitions, right? So the areas of intersection, they happen, yeah, when.
I guess because the non-adiabatic, was it the non-adiabatic approximation broke down when E1 and E2
becomes the same, yeah. So there is no way you can kind of stay on one surface if that surface crosses with the other one, right? And but they can come close to each other, and they're so-called avoided crossing situation. There you can also have transitions, right? And it becomes a matter of energy scale, where the energy gap is small enough for that energy to be accommodated in the nuclear dynamics of nuclear dynamics essentially. All right. So one of the last points, conical intersections, somewhat related. And let's make a quick break before I delete everything and prepare the board. Let's talk about so-called conical intersections.
I hear these are important for chemistry.
They are important for everything, for life.
Oh no. In a chemical sort of life way?
Yeah. Well, life is chemical. You cannot avoid that, right? So, although one may argue that, yeah, life is all about astrophysics, right? But the one that we kind of experience, it's mostly depend on chemistry.
I didn't think I signed my first philosophy. I wasn't so sassy. I was thinking about philosophy. I didn't mean to come across as
No, it's just I will try to I'll keep this short, but anyway, so back to your question, why conical intersections are important, and one reason is that if it's not for conical intersection, then the UV light that comes from sun would damage our DNA very quickly.
But apparently that might not be true.
Yeah. Well, at least that's the common belief because there are conical intersections in the individual nuclei.
But in DNA itself,
Uh-huh.
that might not necessarily be true.
How can you prove that?
That's, I think I'm being reviewed now. Dwayne was mentioning it. I'll tell you
Well, okay, but I can generally tell you that conical intersections are more probable than avoided crossings. Simply the argument would be dimensionality. To have conical intersection, all you need is to have two constraints satisfied. And in proteins, even better. Like you have R, which is huge, right? So 3n minus 6 for a protein is thousands, right? Degrees of freedom. And of course, the dimensionality of the conical intersection will be 1000 minus 2, right? And still huge. But avoided crossings, on the other hand, the situations where you do not have intersections, but rather surfaces kind of avoid each other, it's a minimum on 3n minus 6 surface. And the minimum on 3n minus 6 surface requires you to satisfy all the conditions like energy of I respect to dr. For every component of the R, which are 3n minus 6, they must be 0. So it's like a 3n minus 6 constraints. Right? So this situation is highly improbable. And the situation where the surfaces are crossing, it's highly probable. Now, I can bet my life that DNA, either individual or polymer, will have conical intersection. What people usually miss is the fact that whether this conical intersection is relevant or not.
That's what I meant.
Yeah.
That's what I meant to say.
Yeah.
Like within individual nucleotides, yes.
Yeah.
That's it actually.
They are relevant, but for the DNA they may not be. And the reason is simple. If you have, say, two surfaces and the intersection is somewhere here, but the dynamics is happening somewhere like here, and then it either fluoresces or goes, say, through another surface or another state, this intersection, although it's there, but it's not really relevant, right, to the dynamical process. But they are happening, and okay, now conical intersections. So the way we obtain this cone structure is again by using simple model where we use a crude adiabatic representation, and our Hamiltonian will be as the one which was here, right? This type of Hamiltonian. Now, if we consider matrix element Fi at R0 H R0 plus delta R, right, and then delta R is something small, goes to 0. So we are considering the situation in the proximity of R0. Then we can do Taylor series expansion and for the Hamiltonian, right? So then you have I this electronic Hamiltonian plus dH R plus some higher order terms which we will neglect. Okay, and then this part we will separate essentially our Hamiltonian matrix elements to the part where it's diagonal when H electronic at R0 acts on these functions. They are adiabatic function at this geometry, right? So then the Hamiltonian matrix will be diagonal, right? So then we will have energy, say 1, R0, 0, 0, energy 2 at R0 plus the linear terms, where we'll have, say, phi 1
Is that like the O of
this term.
yeah.
This is a this is a kind of this is a mathematical term for a function that has an order of square, or like if the delta r is small, then square or smaller type of term. So this function, say you can call it f of delta r, it decays with delta r proportional to delta r square. That means that if you take the ratio and limit of that ratio when delta r goes to 0, you will get constant, right? It doesn't mean that the function here is delta r squared. It's any function that has delta r squared term, delta r cubed term, delta r fourth term, and so on and so forth. So essentially the rest of the Taylor expansion. That's how mathematicians in their language, which is more precise, define that this is a type of function that will give you constant when you take the limit of the ratio. And that means it decays not faster than the square. Okay? And there is a small o symbol, which means it decays faster than. So the small o, if it would be small o, then I should write linear term. So it will decay faster than the linear term. But if I use large O, that means it decays not slower. Yeah. All right. Either way, these terms are gone, right? Because we have this first order term, the phi 1 dh over dr phi 2 and then there's a term here to complete the matrix. Now, so then what we can say is that the diagonal terms, phi I, they are just forces that electrons exert on the nuclei based on the consideration that you had in homework, second homework, right? So in the second homework, this energy, say I, which is R, is a function of phi I, H, phi I, right? And then if you differentiate E respect to R, that should be, well, with minus that is a force at our 0 point. Right, and then in the second section, first problem, it's called Hellman-Feynman theorem, tells us that if you differentiate this expression, then you can easily get rid of all the derivatives of the Bryan-Ket, and the only thing which will be left is the derivative of the Hamiltonian, right? So then this can be said as a minus dE over dr for the I, right? And so, and then the off-diagonal terms, we also showed that phi I.
So why is there a minus in front of that?
Well, the gradient of the potential with the minus is a force, right?
Okay.
That's why there's a minus.
I just like if we look at the left hand side.
I'm sorry, yeah, here there's no minus.
Oh, okay. Then never mind. Then
Yeah.
it's good.
I thought you were asking about this minus.
No,
No.
yeah, that
Okay.
one. That one.
Okay. All right. Yeah. So dH dr phi j, and this term is, we saw that this term divided by energy difference will give you non-adiabatic coupling, but then we can write it as a derivative of the function multiplied by energy difference, right? Because if we divide this by energy difference, then it will be non-adiabatic coupling. And let's call this dij. So then our Hamiltonian can be kind of expressed in the dE1 over dr times delta r, then d12 times delta E12 times delta r, and this is vector, this is vector, this is vector, vector. So we have kind of inner product for elements dE2 dr vector multiplied by right. So this is our linear part on top of the diagonal part. This is diagonal part, this is linear. So there will be also the E1 R0 E2 R0 0, right? And so then we can analyze this in terms of just what could possibly be if we assume that some of this in a low dimensional representation, say we have two coordinates, delta r can be delta x and delta y, right? Then usually the coordinates that connect different states are different from the coordinates that are creating forces, as just coming from the symmetry arguments. And so this can be then approximated essentially by having, I'll say, d of x. D is a constant that corresponds to the derivative, and here the derivative of E1 and E2, you can transform things into the form where they are kind of opposite. So it becomes minus D2. The way you can do it is that this expression can be transformed as a plus, E1 plus E2 divided by 2, and E1 minus E2 divided by 2, and then you can transform things so that the derivative will be of the differences rather than of the particular energy. So, or you can think of the picture where E1 and E2 just follow in different directions along the x coordinate, and so then these derivatives will become different. Plus, well, I guess we can do that explicitly. So what I was talking about is E1, right, equals to E1 plus E2 divided by 2 plus E1 minus E2 divided by 2, and then 2 would be with the minus sign here, right? So then the matrix with E1, E2 can be transformed into two matrices. Okay, and this is a constant matrix, don't need to diagonalize it. This one has a positive and negative, but the same components on diagonal. Okay, so then we can okay, so then these deltas, different signs, will come here. Okay, and then for the off-diagonal terms, there's a different coordinates, say cy. So C is the coefficient corresponding to the D21 multiplied by delta energy, right? So we consider this as some kind of coefficient, and the delta R in the direction that couples first and the second state will be y, right? And so then, if you diagonalize such matrix, again, through the quadratic formula, you can find what the eigenstates will be, and they will be, okay, square, essentially plus minus square root, because the sum of these two divided by 2 of the diagonal terms will be 0, so there will be only square roots that are left, c square y square plus dx plus delta, which 1 minus, yeah, so with 4, okay, let me write this here. So if we have delta plus dx minus delta minus dx cy, we diagonalizing it, we're getting square roots of c squared y squared plus 4 delta plus dx squared. It's one diagonal term, and then another diagonal term with minus the same expression. Okay? And so now if these are our adiabatic surfaces, and if we plot them in terms of, well, in the space of x and y, the square root of this like x and y, right, these are our energies, then we would have this conical intersection shape, because the square root of x squared plus y squared, that's the equation for cone. Okay, and here they only have some extra constants, which if you make c and d so 1 and delta say 0, then that will be a perfect cones. And now if you have another consideration here is that if you have only one coordinate instead of two, so say if you have cx off diagonally and x on diagonal, then you will never have intersection, because simply for this to be equal to that, you need to have some point where, well, they become the same, right? Essentially the square root becomes 0. And with two coordinates, you always can find such point. So for the two, like y should be 0 and x should be equal to delta minus delta divided by d, right? Then the square root, this square root becomes 0 and that square root becomes 0, right? And that's the point where the cones meet. But if you, instead of y, only have x, so one coordinate changes the force and the same coordinate couples the states, then this must be 0. So instead of y, there will be x, and you will have condition x should be 0. But 0x will not let you to have 0 here, and so there will be plus delta x multiplied by 2, and here there will be with the same thing with minus, so they will always have a gap in between. Okay, and so the conical intersections appear when you have two coordinates at least, and they have a cone shape because the Taylor series expansion for the Hamiltonian has well, first term is linear usually, okay, in that expression. And so that linear terms, when we diagonalize, becomes a square root of quadratic terms, and that's the equation for cones. Okay, but there are cases where, due to the symmetry, first order terms they become 0. Then you can still have intersections, but then they will become something like a so-called glanced intersections, where the profile is more like parabolic. Okay, so that's also possible, but less frequent, because linear terms are usually there already, and that's what makes conical intersections. Okay, so now the only thing I wanted to say as well is that there is this diabatic representation you may hear about in the context of adiabatic or Born-Oppenheimer dynamics. And diabatic representation is the representation that rotates electronic states so that all these non-adiabatic couplings become 0. Okay, and the motivation for searching for such a representation is that these guys are, well, pain in the neck to deal with, because they diverge when the surfaces intersect, and they have some unpleasant well, kind of divergent structure. That's, I guess, the most important thing, and you want to, well, people would like to avoid in order to do dynamics. The trouble for rotating, say, if you have a matrix that presumably will rotate your states, right? So you have several states, and you want to rotate them so that you will get the other states for which these matrix elements will be 0. It turns out that because this matrix must do that for every r, right? Because there is there's a nuclear coordinate dependence, you just don't have enough variables to satisfy this condition because this is a condition for every pair of electronic functions with one matrix for every coordinate of nuclei. Okay, so diabatic basis that everyone would love to have, it doesn't exist in general, and that is just a matter of showing that the number of equations you want to satisfy is just bigger than the number of elements you can possibly have to rotate the states. Okay. All right, and that's probably all for today.